Welcome back. So, we've talked about the basics of relational databases, but let's be real. When you're building an application, the last thing you want is for your data to get corrupted. I mean, can you imagine losing a customer's order or messing up a payment? That's the kind of thing that keeps developers up at night. So today, we're going under the hood. We're going to look at the hidden promises databases make to keep your data safe, consistent, and, just as important, fast.
Okay, so here's our game plan. We'll start with the fundamental guarantees that protect your data. Then we'll dive into the famous ACID test. It's like a final exam that all serious relational databases have to pass. We'll even see how that compares to a totally different philosophy. After that, we'll shift from theory to practice and talk about a tool you'll use all the time, the ORM. And we'll finish by uncovering a super common performance trap it can cause called the N+1 problem, before we figure out where all this new knowledge fits on your developer roadmap. All right, let's get right to the heart of the matter. How do you make sure that a bunch of related database operations either all succeed or all fail together as one single unbreakable unit? I mean, think about a simple bank transfer, right? You've got two steps: take money out of one account and put money into another. But what happens if the system pulls the money out of the first account and then boom, a server crashes before it can deposit it into the second one? The money is just gone. It's in limbo. This is the exact kind of disaster that modern databases are built to prevent.
And the solution to this problem is a really powerful concept called a transaction. A transaction lets you bundle multiple steps, like our debit and credit, into a single logical package. The database gives you a rock-solid guarantee that this entire package will either complete perfectly or it gets rolled back completely, as if it never even started. It's all or nothing. There's no in-between.
And you know, this all-or-nothing promise, it's actually just one part of a bigger set of guarantees. For decades, the absolute gold standard for reliable transactions in relational databases has been a simple four-letter acronym, ACID. ACID. It stands for atomicity, consistency, isolation, and durability. You can think of these four properties as the bedrock foundation that ensures your data stays correct and reliable even when everything else seems to be going wrong.
So let's break it down really quick. First up, atomicity. That's the all-or-nothing rule we just talked about. The whole transaction works or none of it does. Simple. Next is consistency. This means the database won't let you do anything that breaks its own rules, like letting an account balance dip below zero if that's not allowed. Then we have isolation. This is huge. It means that if two transactions are happening at the same time, they can't mess with each other's data. It's like they're running in their own separate little worlds. And finally, durability. Once a transaction is complete, it's permanent. It's written to disk and will survive a power outage or a system crash. The data is safe.
Now, that isolation property, it's got a bit of a catch. You see, enforcing perfect, total isolation can sometimes slow things down, especially when you have lots of users. So databases actually let you relax the rules just a little bit to get better performance. The trade-off, of course, is that you open the door to some weird edge cases where one transaction might see data that's not quite finished yet. It's a classic balancing act between maximum speed and absolute 100% safety. And this whole trade-off between strict consistency and performance, it's actually a massive deal. In fact, this one idea is so important that it led to the rise of a completely different school of thought for databases, one that's super popular for huge distributed systems. So while relational databases live and breathe the ACID model, many NoSQL databases follow a different model called BASE. That's BASE, for basically available, soft state, and eventual consistency. And here's the key difference. Where ACID puts consistency above all else, BASE says availability is king. It's okay if data across the system is a little out of sync for a short time, as long as it becomes consistent eventually. Okay, so that's enough theory for a bit. Let's switch gears and talk about how we, as developers, actually interact with these databases in our day-to-day work. Because most of the time, we're not sitting there writing raw SQL commands by hand. We're using a really clever abstraction layer. This tool is called an Object Relational Mapper, or ORM for short. And an ORM is basically a translator. It builds a bridge between two different worlds: the world of tables and rows in your database, and the world of objects and classes inside your application code. And this right here shows you exactly why they're so popular. Instead of having to manually write out a SQL query string to find a user, you just call a nice, clean method on an object like users.getById20. The ORM does the dirty work of generating the actual SQL in the background.
On the one hand, this is fantastic. It speeds up development like crazy, cuts down on repetitive code, and often protects you from common security flaws like SQL injection. But that abstraction isn't free. ORMs can add a bit of performance overhead, they can hide what the database is actually doing, and, this is the big one, sometimes they can generate really, really inefficient queries without you even realizing it. And that brings us to one of the most infamous performance traps in all of web development. It's a classic problem that happens when these powerful, helpful ORM abstractions go a little bit wrong.
You've probably been there. You write some code that seems perfectly simple, maybe to display a list of blog posts and their authors, and everything works fine. But then, as your data grows, the page suddenly slows to a crawl, and you're left scratching your head, asking why. Well, the culprit is very often something called the N+1 problem. So here's how the N+1 problem works. Your code innocently makes one query to get a list of items, let's say 50 blog posts. That's the one query. Then you loop through those 50 posts, and for each and every post, your code makes another separate query to fetch the author's name. That's the N queries. So to get 50 posts, you're not making one trip to the database, you're making 51. And this slide right here is the real shocker. It shows why this is so incredibly slow. You might think the database is struggling, but for a simple lookup, the actual work, the CPU and disk time, is tiny, maybe 6% of the total time. The overwhelming majority of the cost, a whopping 94%, is just network latency. It's the time it takes for the request to travel from your app to the database and for the answer to come back. So every single one of those N extra queries adds that full network round-trip cost. It's truly death by 1,000 cuts. All that travel time adds up, and that's what brings your application to its knees. So let's take a step back. We've journeyed all the way from the deep theoretical guarantees of ACID through the practical convenience of ORMs and landed on a very real-world, painful performance problem. Let's tie it all together. Here's what you really need to remember. Think of ACID as your safety net. It's what ensures your data doesn't get corrupted. ORMs are amazing tools for productivity, but they hide the database from you. The key to being a great developer is knowing when to peek under that abstraction. Understanding the why helps you solve problems like the N+1 trap. And the solution is actually straightforward. Instead of making N+1 trips, you tell the ORM to be smarter, to use techniques like eager loading to grab all the data you need in one single efficient trip. Think of this as a checkpoint on your developer journey, really. Moving beyond just using a database to truly understanding how it works, its guarantees, its abstractions, and its common pitfalls is a massive step forward. This is the kind of knowledge that separates hobbyists from professionals who build scalable, reliable applications. Now, let's place it on our roadmap.
This is Developer Roadmaps. Map your path. Build your career.